Hi, in class 6, we started to look at the structure, the three-dimensional structure of proteins, in particular secondary structures, alpha helices, beta sheets, and even random coils. In this video, I want to look at the overall folding of a protein, the thermodynamics, and how the hydrophobic effect helps motivate the molecule or the protein to fold in its preferred native state conformation. And we will look at this protein in particular. This is myoglobin. Myoglobin, shown down here, is a oxygen-binding heme-containing molecule found in muscle tissue. But what I want to focus on here, it's all color-coded. We have green hydrophobic R groups of the amino acids, and we have red hydrophilic residues on the outside of the protein. Let me draw a couple of structures and we can see the difference between a hydrophobic and a hydrophilic amino acid residue. The first two residues I want to look at is valine and tryptophan. These are very nonpolar, and another way we could say nonpolar is that they are very hydrophobic. They do not like to interact with water. They don't have very many dipoles to have an interaction with polar molecule water. This is all taking place in pH 7. Next, I'm going to draw a couple of hydrophilic polar amino acids. The next two amino acids, E, glutamic acid, and K, lysine, those are polar amino acids, but polar and ionizable. So a lot of these amino acids in red, they are going to obtain some charge at pH 7. Oh, also we have some hydrogen bonding, possibly, between water and some of these heteroatoms, oxygen and nitrogen. Let me talk about the ones in black now. The ones in black, the figure terms them as ambivalent, and they have in-between properties between hydrophobic and hydrophilic. They are nonpolar. This is glycine. This is alanine. So glycine only has an H as its side group. They are nonpolar, but they're small enough that they could be partially solubilized, and they're not as hydrophobic as some of these larger nonpolar molecules. In this video, we'll come back to the term hydrophobic and have an explanation of how that helps a protein fold. But right now, I want to look at the overall thermodynamic parameters. So when we talk about delta G, delta H, and delta S, you could just group them all as thermodynamic parameters. But these parameters, they all include actually the delta G, delta H, and delta S of water. So when we look at these numbers, delta G, that is negative. A negative delta G, means that the folding is spontaneous. We have a delta H that is mostly negative. Let me write it here. That's enthalpy. And the enthalpy looks like it's favorable, negative delta H. For the entropy, it's slightly negative, and that is actually unfavorable, meaning that there is decreasing disorder when you fold. When I say the terms favorable and unfavorable, what I'm visualizing is that equation, right? Delta G equals delta H minus T delta S. If you want something that's spontaneous, you want delta G to be negative, or delta G should be negative. To have delta G be negative, it would be good if delta H was negative, right? And then we minus a small positive number. Or just a positive number in general. So typically you want entropy to grow up. And in spontaneous reactions, entropy mostly, not all the time, goes up. But here we have a negative entropy. So that's why I say it's entropically unfavorable, but slightly. And we'll take a look at the components of these in just a bit. Before I talk about the hydrophobic effect, let me just summarize down here what we're really looking at. We have a delta G, and that is going from the unfolded to the folded, the initial state and final state. Okay, folded and unfolded. And that means that we're looking at the delta G of the protein and water. Okay, that's the whole system. While it's folded, right, it's final minus initial, minus the delta G of the protein again, and water when it's unfolded. Since we're talking about water and proteins that typically have hydrophobic residues, I want to go over the hydrophobic effect. Folding is partly driven by what's called the hydrophobic effect. That is the tendency of nonpolar molecules or groups, like R groups, to aggregate or fold to minimize contact with water. The next couple of notes that I'm going to take, we are going to focus on the entropy. This hydrophobic effect is really, the main component of it is the entropy term of the water. And let me jot down a couple of equations for us. Let's look at the delta S for water first. And remember, delta is final minus initial. Our final state is the folded state. And when we look at water, when the protein is in its folded state, the water surrounding that protein has high entropy. We're going to look a little bit more carefully at this a bit later, but meaning that the water molecules around a protein that's folded has a lot of degrees of freedom, has a lot of, it's unencumbered and has high disorder, right? Remember that entropy is a measure of the amount of disorder. The thing is, when the protein is extended, and maybe I could draw it a little bit. So here the protein is like this, but when it's unfolded, it looks like, well, like that. Okay. We're going to learn later in the video that the water has very low entropy. Low disorder, right? So low entropy is the same as saying very ordered. Large number minus a small number, your delta S for the water actually is favorable. It's a very positive when the protein goes from the unfolded to the folded. The problem is, I mean, not a problem, but when we look at the protein side of things, you know, your protein, again, is, when it's folded, it looks like this. Very constricted, right? So I would say this is low entropy. Not much flexibility. Another way you could think of entropy is, high entropy means a lot of degrees of freedom, freedom of movement. But when it's unfolded, like this, it's very floppy. That's high entropy. Well, we have a low number minus a high number, high positive number, so that is very negative. When we look at the delta S total, when we add these two up, it does turn out to be slightly negative, slightly unfavorable, the entropy. But, you know, we are restricting the protein a lot when we fold it. So this water, this favorable entropy of the water, is a very important effect to counteract this restricted motion, low entropy state of the folded protein. Okay, on the next page, I am going to talk a little bit more about this idea that water has high entropy when the protein is folded and very low entropy, very ordered, when the protein is unfolded. I drew a picture here of the unfolded protein. It's a little bit kind of difficult to see, but what I'm illustrating here is that for the unfolded protein, I have hydrophobic residues valine, leucine, and tryptophan, and water surrounding it. right? The protein is dissolved. Well, we have two types of water situations. For the water that's kind of far from the hydrophobic residues, we call that bulk water. And there's very little order. And there's a lot of freedom of movement when they are not pressed up against the hydrophobic residue. That means that these water molecules in bulk water have high entropy. That's good, right? High entropy, high disorder, that's favorable typically. But when you unfold the protein and you expose the hydrophobic residues, water molecules, when they contact the hydrophobic residues, to be able to do that, they have to form very ordered structures to surround the things that don't really want to have contact with water. So the water molecules in pink, when in contact with nonpolar groups, that water has to be highly ordered. Now, that has a special name. You could think of the water as making a cage, a solvent cage around the hydrophobic residue. And there's a special word for that. That's called a clathrate, the situation where you have water kind of forced to order itself and surround the hydrophobic or the nonpolar functional groups. So that's not a very favorable situation because we have high entropy. Oh no, sorry. When it's highly ordered, that means you have less disorder. Highly ordered means less disorder, means low entropy. We know from delta G, I have the table printed out one more time, that it's favorable, spontaneous. And I do have my equilibrium arrow favoring the folded side. Let me jot down a couple of notes about what's happening here now. Okay, it's a little bit crowded. I added a couple of notes here. When the protein is folded, your hydrophobic groups are hidden or aggregated within the protein. So there's no need for these low entropy clathrates, these solvent cages. What does that mean? It means that those water molecules that had first a low entropy, now they have a high entropy because they're not being used as these solvent cages. High entropy. And when we look at the delta S then of just the water, we have high entropy water minus low entropy water. That gives us a positive number. So here we could say ultimately that for the water side of things, entropy is positive. Entropy gains disorder when the protein folds. And that's a very important part of the hydrophobic effect. It's an entropically driven process, and it's looking at the water, basically. So here I focused on the delta S of the water, for sure, and a little bit about the delta S for the protein, right, because it gets more ordered. So for the protein, the delta S is actually negative. When you add those two entropies together, the water and the protein, you do end up with a negative, slightly negative delta S. Let me talk briefly about this negative enthalpy and where is that coming from. Considering enthalpy, endothermic or exothermic, you see the process of folding ultimately is exothermic, enthalpically favorable, and when the protein folds, we get these interactions that do release energy. Electrostatic interactions between a plus charge and a minus charge. We saw that with our two residues here. Electrostatic or ionic interaction. Hydrogen bonding, for sure, can help fold a protein. And dipole-dipole interactions between polar groups that don't necessarily have a formal charge. The last thing I want to talk about, I'm done with the thermodynamic parameter discussion with delta S and delta H. The last thing I want to talk about is when the molecule or the protein unfolds. Another term for unfolds is denatures when you talk about a protein. And the noun is not denaturization, it's denaturation. Denaturation. And that formal definition is the loss of structural integrity with accompanying loss of activity. So the protein becomes unfunctional. There are a couple of factors that could cause a protein to denature: heat or cold. Well, when you heat up a molecule, it moves faster, there's more energy, so you can start to disrupt your interactions that gave you that negative delta H when it folds. It disrupts hydrogen bonding, electrostatic interactions, even hydrophobic interactions, right? The motivation for two nonpolar residues to come close together to exclude water, well, if you give them more energy, they're more likely to separate. And, whoops, that's that should be an N, van der Waals forces. London dispersion forces also is another way to say it. What about the cold, though? The cold, you can imagine, it kind of freezes the protein, makes it less flexible, and maybe it might get stuck in a local minima instead of the global minimum. So you get suboptimal folding. You'll have some folding, but it's maybe not the correct folding. And you really need the protein to have enough energy to be flexible enough to survey different interactions to finally get to what's called the native state, or the proper folded state. And in that native state, you could think about the conformation or the energy as the global minimum. You have a global valley like that. So you want to attain that state, most stable state, folded state. Now, when you talk about pH, if you have very acidic, right, or if you have very basic pH, then you will start either protonating everything or deprotonating everything, and you'll start to disrupt the favorable electrostatic interactions. Organic solvents can cause a protein to denature because organic solvents are the opposite. These are nonpolar molecules, and they can solubilize nonpolar or hydrophobic amino acids. Thus, you are negating the hydrophobic effect if you dissolve your protein in like chloroform instead of water. Chaotropic agents. So chaotropic agents disrupt hydrogen bonding of water. And when you do that, you're decreasing the hydrophobic effect. It's not as pronounced when you can start disrupting the hydrogen bonding of water itself. So it makes folding less favorable. So a chaotropic agent is, for instance, urea. Urea looks like this, and you can imagine how that molecule can disrupt hydrogen bonding of the water. Next, UV radiation. This is not typically known, but UV radiation can also denature a protein. One mechanism is it causes electron transfer in cysteine residues. And when you have electron transfer, uncontrolled electron transfer, you will start breaking up the disulfide bonds. And you understand that disulfide bonds is considered one of the primary structures, and it helps fold a protein. Lastly, we have detergents. Detergents are what's called amphiphilic, meaning that they bind polar and nonpolar groups, and hence your protein can be stabilized in the unfolded state because you have, for instance, these hydrophobic residues. Well, instead of them being surrounded by water, which causes very low entropy, disfavorable, you'll have a detergent. And the detergent could be a very long carbon chain, and you have a polar group, which can interact with water. But basically, the detergent is itself hiding the hydrophobic residues. So there's no motivation, or less motivation, for this to fold up to hide the nonpolar amino acids, because they're hidden already by the detergent.